Hello, chemistry students. This is our lesson on converting from grams of one molecule to grams of the other when these molecules happen to be in the same chemical formula. You will often see this as someone needs to carry out a chemical equation, some chemical reaction, and they want a certain amount of product. They want a certain grams of that product. And in order to do that, why waste your reactants? Figure out how many grams of each of the reactants are required, especially when those reactants are very expensive or very rare. You're going to see this. Any business, any science, they don't want excess of anything being wasted. If you're engineering something, if you're designing a medicine, those extra things might not just be wasteful, they might be detrimental to the design you're trying to do. So often we want to create precise reactions that use exactly the amount we want. To do this grams to grams, it is definitely the most relevant for that reason. I am going to give you this silly example from The Martian. In that book or movie, whichever you happen to see, the main character is trying to grow some potatoes because he got stranded on Mars, but needs some water to water them. They won't grow without it, and Mars is not a wet planet. The main character does have oxygen from an oxygen generator. It carries out a different kind of chemical reaction, and is able to rig a hydrogen generator from a different contraption. So he has hydrogen and oxygen. However, let's assume he doesn't want to use up all of his oxygen. That would be detrimental to life. So we want to be very precise with exactly how much oxygen is being used. For the sake of numbers that we can solve, let's assume you want to produce 2,000 grams of water. How many grams of O2 will be required? You can see our synthesis of water equation up here. Water is the product. Oxygen is one of the reactants. For the sake of this, we're not going to worry about hydrogen. We're going to assume we have plenty of hydrogen. So hydrogen is in excess. To set this up, first, let's figure out our given. I'm going to highlight in red, 2,000 grams of H2O. That's my given. If that's what we're given, then what are we trying to solve for? The thing we're trying to solve, given. The thing we're trying to solve for, I'm going to highlight in green. We are trying to solve for grams of O2. So this is solve for. Both of these are saying grams. So grams and grams, we have mass and we have mass. To get from mass of one molecule to another molecule, first off, they have to be in the same chemical equation. O2, that's right here. H2O, that's right here. Good. First thing met. Next, we will need 3 different conversion factors. 3 conversion factors. If you're one of my students, you've already done some silly ones for this. I said, whoa, if you had US dollars, convert it to Saudi Royal first. Then from Saudi Royal to Thai baht. From Thai baht to Chinese yen. This is as hard as that. It's no harder. It's chemistry related, but it's the same thing. You need 3 different conversion factors for that. Let's set this up a little more meaningfully. If you keep following what I set up next, all that changes is the molecule, but the format, the formula essentially is the same thing. So you have a given number of grams, that's your mass. So you have grams H2O. You are trying to convert that to, do it in orange, moles H2O. From there, because we cannot go directly from grams to grams, we're going to convert that again. But this time to moles of the other molecule, O2. Finally, we are going to convert that one last time to grams, or mass, of O2. Each of those arrows represents a conversion factor we need to get from grams to moles of water. Turns out we need something you're already very familiar with. We need the molar mass of, in this case, H2O, because that's what we're trying to use here. Grams to moles of water. So you need molar mass, specifically of water. This next one, we're going from moles of water to moles of oxygen. As long as they are in the same chemical equation, we just need the coefficients from a balanced chemical equation to solve for that. Coefficients from a balanced chem equation. Final one, from moles O2 to grams O2. It's all O2, and instead of going from grams to moles, we're going from moles to grams, but thankfully, same concept. We need molar mass again, but this time it's water. Sorry, not water, it's oxygen. So this needs to be the molar mass of O2. Not just O, but O2, because this is moles O2 to grams O2. Again, this is the format you will always follow. From grams to moles, using molar mass. From moles to moles, using coefficients. And from moles to grams, using molar mass. So let's set this up. I'm going to start it by giving the actual amount of grams that I'm given in the problem. So here we have 2,000 grams of H2O. I'm going to start with that. 2,000 grams GH2O. And now I need to multiply by that first conversion factor, molar mass of H2O. Then I need to multiply by the next conversion factor that contains coefficients from a balanced chemical equation. Then I need to multiply by a third conversion factor, the molar mass of oxygen, to get to our final solution. Before plugging any more numbers in, I just want to align my units. Remember, your given is a numerator. It's really over 1. So if grams H2O is in the top, I need grams H2O in the bottom, at the denominator, the first conversion factor. I'm trying to get from grams H2O to moles H2O, so on the top is going to be what my target is. My target is moles H2O. If you can't remember the top-bottom thing, another way to remember it is on the bottom is the unit you're converting from. On the top is the unit you're converting to. From grams H2O to moles H2O. From moles H2O to moles O2. So on the bottom, moles H2O. And on the top, moles O2. From moles O2 to grams O2. Therefore, on the bottom, from moles O2 to the top, grams O2. Let's see if everything cancels out the way it should. Top units cancel bottom. Top cancels bottom. Top cancels bottom. We are left with grams O2, which is what we want. Grams O2. So Should check all the way back to solve for grams O2. Good. It's the only unit that doesn't cancel out. I'm going to get rid of those crosses just so we can clearly see the units. All right. Now for the numbers part. Our units are good. We just need the numbers to be good. For the first one, molar mass of H2O. You guys know how to calculate molar mass. In this case, water consists of 2 hydrogens. So the molar mass of hydrogen times 2 plus water consists of 1 oxygen. So it just consists of oxygen, or oxygen times 1 if you want to follow through as much as that. I have copied in the periodic table squares just so you can see where I'm getting the numbers from. H 1.008 and oxygen is going to be 15.99. So plug those in. 1.008 times 2. Close the parentheses and add it to the mass of oxygen, 15.999. Times 1 is the same thing. Solve that, and you end up with 18.015 grams per 1 mole, or grams per mole. Transpose those numbers up. The 18.015 grams is going to be on the bottom, because I see grams there on the bottom. So 18.015 grams. On the top, I need moles H2O. And saying grams per mole is the same as saying grams per 1 mole. It's just one of them. So up here, it's per 1 mole. Scroll over. Next thing to tackle. We need coefficients from a balanced chemical equation to get from moles H2O to moles O2. I have an unbalanced chemical equation up here, so that's useless. We need to balance it real quick. Remember, when they're left blank, they're assumed to have a coefficient of 1. So balance it. H would be 2 and O would be 2. H on the product side would equal 2. O on the product side would equal, 1. So oxygen is unbalanced. So let's change the coefficient from 1 to 2. If I change this to 2, now I have 2 times 2 hydrogen. I've got 4 hydrogens. 2 coefficient times 1 oxygen gets my oxygen up to 2. That did throw off your hydrogen balance, so now I have to go back over to the reactant side and adjust hydrogen. Change that coefficient of 1 to a coefficient of 2. 2 times 2 gets me to 4. My hydrogens are balanced. 2 times 2 is 4. 2 times 2 is 4. My oxygens are balanced. 1 times 2 is 2. 2 times 1 is 2. Now, bring those numbers down. First, I'm seeing moles O2. So, if O2 is down here, find O2 up here. Find the coefficient. That one was one that remained 1. So, 1 goes there. The next coefficient I need is for water. So, find water up here in the equation. H2O. The coefficient there is 2. So, bring the 2 down. We'll have a 2 there. Finally, molar mass of oxygen. Well, to do that, I need oxygen times 2, because in this case, there are 2 oxygens in every molecule of oxygen gas, or O2. So, again, I've got my periodic table, just what I need removed from it. I will have 15.999 times 2. And that's it. That leaves me with 31 when I solve. 31.998 grams per mole, or grams per 1 mole, however you want to look at it. Bring those numbers up. 31.998 gram. That is going to be in the top. 31.998, because that's where grams are. I see here I've already put grams O2 in the top. But I need per mole. And down here it's 31.998 gram per 1 mole. So drop a 1 in there. Next, condense this. In order to condense it, I'm just going to take all the numerators, which includes the given whole number, so the 2,000, the 1, and the 31.998, and multiply them together. So 2,000 times 1 times 1 times 31.998. Now, condense the bottom before I bother solving. Got to condense the bottom denominators. 18.015, the 2, and the 1. Condense them so that they're all multiplied by each other. 18.015 times 2 times 1. If I just do this in a stepwise fashion, I will solve the top and solve the bottom. The top, the product is 63,996. Solve for the product of the bottom, and we get 36.03. Finish this one last time. Top divided by the bottom. You end up with 1,776 grams of oxygen. How'd I know to say grams of oxygen? Because that was the only unit that survived up top. I wanted grams of oxygen. I got grams of oxygen. Before you completely finish, make sure those answers make sense. You were aiming for 2,000 grams of water. Water is the product made up of partially oxygen and partially hydrogen. So then your substrates better be smaller than the only product that was produced. In this case it is. It is a very large amount of the mass. It's almost all of the mass. So make sure that makes sense. Oxygen has way more mass than hydrogen. Each oxygen atom is 15.99. Each hydrogen is only 1. So it would make sense that it has the majority of the mass. That is it for this. If you are my students, or if you're not, the next video will do a small walkthrough where I'm going to set you up step by step, encourage you to pause, do it on your own, check your answers, and then try the next. And we'll go through stepwise till we finish. Good luck. Thank you, Chem students.